Afternoon, everyone. I've started recording. Where are we? We're lecture 4. I can read that now, which is going to be Ferenc on stochastic optimization. As always, put questions in the chat. I'll be monitoring the chat and we'll interrupt Ferenc if it seems sensible, or we'll try and answer them as they come in. Over to you, Ferenc.
Okay. Do you think people who should be here are here already? Okay.
Yeah,
so
we've got
everyone...
34 in the meeting, which is around about what we'd expect. Yeah.
Thanks. So hi, everyone. This is the 4th lecture of the Deep Neural Networks course. And today I'm going to talk about stochastic optimization, which is pretty much most of what deep learning is about, in my opinion. There is, of course, a lot more to it, like architectures and many other things. But in many ways, I think stochastic optimization is what seems to explain many of those interesting phenomena that we talked about in the last lecture. So last time when I talked about calculating gradients, I had this iteration here as an example of what gradient descent looks like for a neural network. I have some current parameters WT. I kind of stuck with W because that's what Neil used in his lectures, and I tried to be consistent with it. But in the literature, you will find theta being used for parameters much more often in the context of deep neural networks, and we will see it in one of the slides. It's going to be denoted by theta. So we have our current iterate WT, which is where the neural network parameters are now. And we are going to take a small step, eta being a learning rate parameter, which is small, in the opposite direction of the gradient. So we're calculating the gradient of the empirical loss function. This L hat was the empirical loss. And this is how we get the next iterate WT. And we keep iterating this until the process converges or until we find a parameter setting that no longer improves our held out validation set performance, for example. I'm going to talk about stochastic optimization, which is not actually what's written here. And that's because calculating this gradient term here is very difficult, and it's not what we actually do. First of all, in order to calculate this is a big sum over our entire data set. So curly D is our data set, which consists of n observations. And this L hat becomes a sum over all of those n observations. And if we have a large number of observations, iterating through all of it is just too time consuming. Also, if we want to calculate this gradient on a GPU, which I think Nick might talk about next time when we talk about hardware, we would have to fit this data set into the memory of the GPU in order to start this calculation. And so there's a limit on how much of the data you can even put into the GPU's memory, or if you use any other computing architecture, there might be a similar limitation of how much data you can reasonably process within the memory of that device. And finally, we don't actually need to use the whole data set here, because L hat is a sum over all the data points, or an average over the loss of many data points. So the central limit theorem applies, which means that even if we calculated just a small percentage of the data set, this average loss wouldn't change after a while, because it would essentially converge to the loss over the entire data set based on just a smaller subsample of the data set. So what we do in practice with neural networks is what's called stochastic gradient descent, also sometimes called specifically mini-batch stochastic gradient descent. And what has changed from the previous slide is that now I evaluate this loss not on the whole data set, but on a particular subsample of my data set. So DT is a random subset. It's called a mini batch, which is sampled from the large data set, the training data set that I have access to. A lot is hidden behind this notation. So this DT is in fact a random, you can think of it as a random variable. And so at least mathematically, every time you update with your gradients, you pick a random subsample from your data. In practice, when you do this, you usually just cycle through chunks of your data. You don't actually have to, run random number generation and randomly subsample your data set at every time. But from a mathematical perspective, you are taking a random subsample of your data. And because this random subsample of your data is called a mini batch, so we are talking about maybe in some cases 100, in some cases maybe up to 1,000, in some cases even higher or larger number of data points in each of the mini batches. Because this small data set or portion of the data set is called a mini batch, this is called a mini batch stochastic gradient descent. The first question that I wanted to look into it is, does this process converge? We know that gradient descent, this thing without the random subsets, always converges to it can get stuck in very unfortunate situations, but in general it converges, and the iterates kind of stop at a particular location. So you know that this iteration will lead to somewhere, and typically it ends up in a local minimum of the empirical loss function. But because here in every single step, we take a step in a random direction because we use a random subset of our data, do we have similar guarantees that this process is also going to converge in some sense, or that this process is going to lead to a particular location or a particular loss function value, rather than just wander around randomly in space? And I'm actually going to show this on paper. I will upload notes for this. There's no notes uploaded right now, but hopefully in a couple of days there will be. So I'm just going to show this by hand today. So one thing that is important about the stochastic gradient, can everybody see my hand and my paper? Yeah. So the stochastic gradient is the empirical loss evaluated at the parameter W and at a random subset of my data dt. And what I can say about this is that if I take the expectation of this gradient, and the expectation is meant under multiple random subsamples of my data, so the randomness enters in how I subsample my data. If I take an expectation over the distribution that defines that randomness, this is the same as the empirical loss. It's not difficult to show, and this is essentially, you can think about this as if you have, this is the average loss on small chunks of your data. If you average the averages, you get the overall average over your whole data set. And this is referred to as my gradient estimator being an unbiased estimator of the gradient, which means that its expected value is exactly the thing that I want, which is the gradient over the whole data set. And this property is important in ensuring that stochastic gradient descent converges. And in fact, in this case, I'm using a subsample of my data to construct an unbiased gradient estimator. If you have other ways of constructing unbiased random estimators of the gradient, the same kind of argument that I'm going to talk about now holds for arbitrary random gradients as well. The first thing that we need to think about is what happens after a single step with a single step of gradient updates. And one thing that we can say is that the expected value of the empirical loss of WT plus 1 at the whole data set, so this is the empirical loss over the whole data set, given the current iterates WT and all the previous iterates t minus 1 and so on in general, so W0. We can say that this expected value is smaller than the loss of WT on the whole data set. So this conditional expectation is it depends on the history of my iterates, and if WT is a particular value, I can look at, on average, do I reduce the value of my loss function? So is it true that the average value of the loss at the next iterate is always smaller than the loss at my current iterate WT? And this is true for the following reasons. If you have a loss function, I'm just going to illustrate this on a one-dimensional example. So I have, say, W on this side, and I have L on the y-axis. And this is WT, let's say here. And what I can, and this is the loss of W as a function of W on my mini batch dt. What I can say is that locally around WT, if the curvature of my function is small enough, this function looks like its first order Taylor approximation, which is essentially the best linear approximation I can make to this function that touches this function at exactly at the location WT. And this function looks like L hat of W t plus W minus WT times L hat of W dt. So sorry, this is the gradient of this mini batch loss. This is the Taylor approximation, which is the 0th order term. That's just the value of the function at the point around which we take the Taylor approximation. And the second part is the gradient times the difference from the point where we take the Taylor approximation. And this is going to be a vector, so it's difference transpose times the gradient. So what we can say is that the loss function at WT plus 1 dt is roughly the same as the loss function of WT at dt. So I'm just using this formula here, plus W minus WT WT plus 1 minus WT times this gradient, W transpose. This is gradient of the loss function at WT. I leave out the dt here because there's no more space left. And what I can say about this is that, so now I can use the formula for stochastic gradient descent, and I know that WT plus 1 minus WT is negative learning rate times the gradient W with respect to W of L, W, T, and the mini batch. If I substitute this in here, and I'm going to kind of speed this up and just skip a couple of steps that I'm going to put in the notes. If I substitute this formula back in here, I basically get an inner product between the gradient on the mini batch and an inner product again with the gradient on the mini batch. But I can do this same reasoning without a mini batch and on the entire data set. So I'm just going to delete the D's. And what I essentially have here is for the iterate to improve my my loss function, or to remove my loss function, I will need this gradient on average to have a positive scalar product with this gradient. So I want that on average, WT, sorry, the gradient with respect to W of my loss function on the mini batch. I want this to have a positive inner product with the gradient of the empirical loss on the whole data set. And if this is unbiased, then we can say that this expected value is the same as this gradient here. Then, of course, the inner product of a vector with itself is its squared norm, so it's always positive. So we can lower bound it by 0. And because we could lower bound this by 0, we could essentially ensure that in expectation, the empirical loss of the iterates is expected to go down. It doesn't mean that it always goes down. Sometimes it can increase, but the expected value of the loss of the next iterate is always lower than the loss of the current iterate. And this property,
just because we had a lot of questions about, feels like there's a lot of people that have fitted neural networks and have been asked what the batch size, mini batch size should be, because there were some very specific questions on that. Yeah. And I was trying to get across that there's some intuition here, and I wonder if it's okay with you just to interrupt and maybe say a little bit about that variance and how that's affected by the mini batch size and sort of the intuition for people on how to set that.
I'm gonna speed this up. That's basically what I'm gonna talk about next, but I kind of bogged down into details of showing the convergence a little bit. So yeah, let me conclude this, and then I'm going to move on and also react to the point that you're saying about how do I choose the batch size.
Thanks, French.
So one thing to note is that this property is important because it means that the loss at the iterates of stochastic gradient descent is something called a super martingale. A super martingale is basically a random sequence that in expectation is decreasing. That's a very hand-wavy way to put it, but that's essentially what we are looking at here. And if I go back to my slides, we are going to hopefully see if I find where my slides are.
Another thing that came up, just while you're moving your slides, is how much work is there on estimators that are biased? I know Max Welling, in terms of Monte Carlo, has sort of done some really nice work on, well, actually, sometimes I'm happy to sacrifice biasness for variance, because in a very high variance case, I don't move towards the solution either. And if I don't have much compute time, and I know I'm not going to manage full convergence, I might be prepared to get closer by going for an algorithm. Is that also an algorithm that is biased but lower variance? And I know that happens in Markov chain Monte Carlo, or Max Welling's brought that idea up. It's not popular with statisticians.
Yeah, so, okay, but, so I'm going to conclude this. Basically, you can say that because it has this super martingale property, that is the key to understanding why this converges, even though it's random. So if you have a version, for this type of convergence theorem, in theory, it's important that your gradient estimator is unbiased. But it is true that you can use biased but lower variance estimators, and sometimes they also work in practice. For example, if you work with neural networks that have non-differentiable parts in it, it may be impossible to get an unbiased estimator of the gradient. And sometimes people use biased estimators, and they seem to be working just fine in practice. In terms of how large the batch size is going to be, I will return to that question later, because I want to talk a little bit about the importance of gradient noise in general. And also, I just wanted to point out that in this lecture, I'm going to be talking more about kind of the intuitions behind stochastic gradient descent, And I could spend probably several lectures just to go through all the practical and pragmatic tricks that people have developed over time to make these methods work best, and how do you choose those hyperparameters, and how do you tune them in practice. I will try and give you good pointers if you want to learn more about those things. And it's also something that people pick up intuition for through experience of trying to solve different problems and seeing what kind of approach works in what situation. So we know that stochastic gradient descent will converge to something because of the Martingale convergence theorem, but does it actually behave the same way as running gradient descent without the mini batches? So it's also called full batch gradient descent. And for this, consider two situations. In both of these situations, I'm showing an average loss function that is the same. So this is the yellow function. But in one case, this average loss is the average of a bunch of loss functions for each of the batches, which are relatively similar. So on the left-hand side, I see that within individual batches of data, I have very good estimates of this average loss. And most of these batch-wise losses are going to tell me the same thing about where the optimal parameter is. And if I run gradient descent, basically in every step, I choose a different color curve or a different curve from a different batch to tell me which way to go, so which gradient to use. And the way I drew this is of course a cartoon example, is that all of these curves are going to basically point me in exactly the same direction. So in this situation, when you have a minimum where all of the batches define exactly the same loss or very similar losses, there is very little variance in what these different batches tell you about the parameters, gradient descent and stochastic gradient descent will roughly work in the same way. However, consider this other scenario on the right-hand side where I can make the same average loss function out of very, very different, as the average of very, very different loss functions. So here I drew these 4 loss functions. Obviously, this is not going to be exactly the mean, but you can imagine that all of these different loss mini batches of data will define a loss function that's very sharp. It has a minimum at a slightly different location, and outside of this minimum, it has much, much sharper sort of sides, which means that the gradients are going to be much higher. So if I try to run stochastic gradient descent around this region, what I'm going to see is that depending on which ones, let's say that I'm here, depending on which one of these batches I am evaluating, some of these batches like this one and this one is going to send me to the right, and it's going to have a rather large gradient sending me to the right. And if I look at this or this curve, well, in the purple region, I would probably be around this minimum, but this blue curve would send me in the complete opposite direction to the left. So in the situations where the loss functions on different batches have a high variance and they are very different from one another, stochastic gradient descent will have a hard time converging. So some of these large gradients that you get from one of these curves is eventually going to catapult you out of this region. So we should expect that stochastic gradient descent might have a preference for regions of the space or local minima that behave more like the left-hand side figure, and is going to potentially avoid or will have a more difficult time converging in a situation that's depicted on the right-hand figure. So if I was in the classroom, I would probably now poll people, which one of these minima do we think are better? So if we were to pick one of these minima from the perspectives of machine learning, so generalizing better to unseen examples, I will give you just a couple minutes or just a minute to think which one of these would be probably preferable. I will look at the chat in the meantime. So you can write in the chat left or right if you have a view on this. Answers here, yeah. Anyhow, I'm not going to wait for those responses. In my personal opinion, and this means that there is no, I don't have any particular proof to offer, the left-hand curve is probably, the left-hand situation is probably preferable to the right-hand situation. Because if my loss function is very sensitive to which particular mini batch of data I'm working with, it's probably also going to be very sensitive to whether I evaluate the loss on the training set or whether I evaluate the loss on the test set. So if there can be huge differences between losses on different mini batches, that means that there probably can be large differences between training loss and test loss, which means poor generalization, or sorry, yes, which means poor generalization. So in these cases, because there are large differences between losses evaluated on different mini batches, I would also expect that, that this minimum would generalize more poorly compared to this minimum where the variance is much smaller. So this has been my intuition about why stochastic gradient descent might actually prefer minima that, even though they have the same training loss, so assumed in this cartoon illustration that both of these functions, the average loss has the same level of minimum, so you achieve the same performance in each of these minima on the training set, they might have completely different generalization performance, and that stochastic gradient descent might prefer the one that potentially generalizes better.
Friends, question from me.
Yes.
So I have the same intuition with you as you. And I sort of hinted at in my lecture some of the gradient flow methods people have used to analyze the generalization performance. And it sort of interests me a little bit that none of those methods are actually representing what stochastic gradient descent does. Have you seen, I haven't seen yet, sort of methods that manage to capture this intuition alongside some of those papers that we were citing
That's
in the first
that's
lecture?
what I've just put on my slides. That's the next thing I'm going to talk about. Yes, I think what Neil is pointing at is that some of those techniques that we both talked about in our previous lectures, like neural tangent kernels or deep linear models, I certainly talked about deep linear models, try to explain why deep learning works so well without using stochastic gradient descent. So those are those explanations for why deep learning works essentially use full batch gradient descent as in their papers or in their explanations, which means that there are explanations that do not include stochasticity of the gradients as to why deep learning generalizes well. And it probably means that this magic sauce that makes it work has multiple ingredients. So one of the ingredients, in my opinion, is this stochasticity, which I'm going to talk about next. And another potential ingredient is the overparametrization, which is what the NTK regime or the deep linear model work neatly illustrates. So along these lines, I wanted to show you a very recent result that captures this intuition that we just talked about here. And this analyzes the mean iterate of stochastic gradient descent. And what these figures are meant to show, on the left-hand panel, if we have a loss function which is two-dimensional, batch gradient descent takes steps along deterministic gradients. So basically you go from here to here to here to here and so on, and you essentially eventually converge to something. Stochastic gradient descent calculates a random gradient at each step. And so even if you start from a deterministic point after just one step, you are in a random position. And depending on which particular subsample of your data you picked first, it determines where you are within this illustrative distribution. And as you keep using these stochastic gradients, eventually you accumulate this noise from the gradients. And so at every given time step, you don't just have one deterministic location where gradient descent ends up. You essentially have a distribution over possible places that stochastic gradient descent can take you if you randomize the order in which data is presented. And this makes stochastic gradient descent pretty difficult to analyze. So what this paper, Smith et al., which is going to appear at a conference this year, what they have done is let's look at what the mean of this random distribution does at every time step. So this ellipsis here illustrates that after 1, 2, 3, 4, 5, 6, maybe 7 steps, these are the probable regions where the iterate might be. Let's just look at the mean of this distribution. And I'm gonna, so those who are already annoyed by taking the mean, you're probably right. I'm going to talk about this in the future. But let's just look at the mean. If I look at the mean, this is called the mean iterate of Sgd. Now I have a non-stochastic trajectory. So now I have a deterministic trajectory once again, because I don't care about the randomness. I just look at where you are, where you end up with stochastic gradient descent on average. So I don't know why my equations ended up so small here. If you have this stochastic gradient descent, what we are looking at here is essentially the expected value of Wt, where the expectation is taken under different ways in which you can subsample data points in all of the previous steps that have led up to time step t. And I'm going to call this mu t. This is the mean iterate at time t. And what this paper talks about is that this mean iterate can be approximated or well approximated as a continuous gradient flow. So this is a little bit involved, and you don't necessarily have to understand this all. This is an approximation where in gradient descent, we take discrete steps. So step 1, 2, 3, 4, 5. You can imagine instead that time is continuous, and instead of hopping around in parameter space in discrete times, you are kind of shifting around smoothly in space. So this mu of t, where t is now continuous, is a function of time, of what's the expected value of the parameter at time t of running this process. And you can model stochastic gradient descent as this continuous flow, which is the gradient of mu, which is the mean iterate, is minus some step size, nu, or eta, times the gradient of a modified loss function. So this L tilde Sgd here is not the same as the empirical loss, but it's a modified loss function. In other words, you can approximate the evolution of the mean iterate of stochastic gradient descent as if it was gradient descent, but not on the original loss function, but a modified loss function. And this equation down here shows how this loss function is modified. This loss function for stochastic gradient descent is the loss function for gradient descent. So this is if you run gradient descent without the gradient noise, plus learning rate divided by 4 times what is essentially the variance of the gradients across different mini batches. Finally, my equations are back to the intended size. So here we have the gradient on the mini batch dt. Here we have the gradient on the entire data set, which is the mean of the gradient at mini batch dt. So this is the norm of the difference between the random variable and its mean, and you take the expectation of it, so you essentially end up with something along the lines of the variance. It's in higher dimensions, it's the trace of the covariance matrix. So coming back to this previous idea, we can using this argument, we can say that stochastic gradient descent is a little bit like running gradient descent, but with this extra quote unquote regularization term. And note that this is a data-dependent regularization term, and it essentially tells you what is the variance of the gradients at this particular location in parameter space on your data set. And so if you run gradient descent on this regularized loss function, you will try to avoid regions where the variance of the gradients is high, and you will try to converge to areas of the parameter space where this variance is low. So returning to the cartoon example, this extra loss term that a stochastic gradient descent implicitly introduces will make this minimum look a much better minimum. It's going to be a lot easier to converge to this local minimum, and it's going to be a lot harder to converge to the local minimum on the right, because the variance of the gradients would be much higher here. And this new work essentially makes this intuition very explicit, and to the point where you can mathematically say that it's there is this extra term in the loss function that penalizes you for high variance gradients. I'm going to stop and see if there are any questions, or Nick, if you've seen anything that.
There was an earlier question for Nick, I think targeted more at Nick, which is, but also maybe at all of us. I had a slightly facetious reply. Why are the mini-batch gradients often in powers of 2?
Yeah.
Or mini-batch sizes, sorry. Mini-batch.
Yeah, so I think that's partly cultural, because it's the geeks, picking those numbers. And then also partly, there might be some rationale behind the size of the memory.
Is the hardware rationale behind that, Nick? Or
yeah, there would be a hardware rationale, because it's just easy to fit everything. I mean, it's kind of the units that we work with, and so it's a challenge in general to map these things into memory and have them in the right place. And so if you have a lot of sort of dangling, if you partially fill something and then try to operate on it, you pay the cost of the whole thing. Typically, is one way to say.
What sort of thing? I'm intrigued that, because I sort of had the same type of answer as Ferenc. I think, well, lesson number 1, if you are going to pull a parameter out of the sky, make it look plausible, like 1024 or 512 or 256, because you're less likely to be questioned on it by your reviewers. But yes, as you say, you can imagine there's a hardware reason. But do you think, which way round is it going? Is it just convenient that people have chosen those things to retrofit with the GPUs, or is for particular GPUs, can we say what that number should be quite easily at the moment?
I mean, we could say what the number should be for a specific setup, but I think in the frameworks you can still specify, sort of unusual numbers, and then because some people it's like the thing that jumps to my mind is the size of a kernel in a CNN. Maybe you might like have 3x3 or 5x5, but then there can be a pain to lay that out. There are other ones that are easier.
What I'm suddenly thinking is that I can imagine a little assignment task, which is to vary the mini batch size and see if there's discrete jumps around any of these numbers actually over the time it takes to run a fixed number of iterations. Would that be a valid thing to try and do?
Yeah, although and I think the more direct route would be, it would be to there's certain things you can change in the architecture that you would say, you increase the architecture complexity by sort of say 1%, and then you look at the overhead on your machine and you're like, oh, well, why is it just doubled? And it's because you maybe crossed over some boundary. That definitely happens with memory in the describing the whole thing.
I think I think though that even if those hardware boundaries no longer existed, my prediction would be counterfactually, people would still be picking factors of or powers of 2 just because of.
I think you're right, Ferenc. Yeah, but I think it's
a cultural.
Robert has a question. He's saying, are we saying that the left-hand minimum better generalizes, or that SGD has an easier job reaching the left-hand minimum than the right-hand minimum?
Yeah, so basically we are saying both of those things, so I'm saying that because so you can think of this left-hand image as saying that your loss function at this particular location isn't very sensitive on how you subsample your data, and this probably implies that if you think about comparing performance on the training set and versus a test set, which you can think of as 2 very large mini batches, the minima on the test and the training set are also probably closer to one another here than they might be over here. I think that you can probably make some kind of more precise statements about this. So there are two things we are saying. We are saying that minima like the left-hand side are probably preferable from the perspective of generalization. And we are also saying that stochastic gradient descent tends to converge to minima that look more like this. And these two statements kind of explain, at least partially, why stochastic gradient descent has a beneficial effect on generalization, because it tends to prefer these minima, and these minima tend to generalize better. At least that's the current intuitive thinking about this. So I hope that answers the question.
A follow-up on that, which is, do we use the same data set for both graphs and simply screw up stochastic sampling on the right-hand side, or are these two different data sets?
So I drew them. They are not data sets, just to make sure. These would be the same data sets, but around different minima. So maybe I wasn't clear about this. In general, in neural networks, this loss function, the average loss, is going to be non-convex, and is going to have multiple local minima. And as I talked about in the last lecture, the key question is going to be not whether you converge to a local minimum, but the key question is which one of those several very good local minima do you end up picking? So what I'm imagining here, and maybe I shouldn't have put two sets of axes here, is that these are two local minima of the same loss function, but at different regions. And maybe in this region of parameter space, where this left-hand minimum is, in this region of parameter space, you're not as sensitive to mini-batches, whereas around this other minimum, which is somewhere else in parameter space, you are more sensitive. And what I'm saying is that you could converge to each of these local minima. These are both, let's assume, local minima of the same loss function. In terms of average loss value, they would be equally good, but probably the left-hand side minimum would be preferable. So if you can design an algorithm that prefers converging to the left-hand type of local minimum, that's probably going to overall lead to better generalization. And that seems to be what's going on with stochastic gradient descent.
When I'm looking at your graph here, for instance, so I should let you push on if there's more stuff you wanted to say, but I'm conceptually thinking that the scale on the right-hand side is narrower. So although the orange curves look the same width, I would be thinking, oh, that's probably a narrower minimum. And that explains why, so if you think the batches are equally widely distributed apart, if the minimum was narrower, then you would be back in the situation on the left-hand side, it would look like the right-hand side. So and another way of thinking, I think about what Ferenc is saying, is that basically you're not going to end up in narrower minimas. You're going to miss them because would that be roughly right?
Well, so I think
curvature would be tighter, I should say.
I could probably talk about this a long time. So there are, what you're identifying here is that there are two independent things going on here. There is the width of the minima, which is essentially, you can think of it as the Hessian of the average loss surface. And then there is, even if those are the same, or you kind of shrink space or stress space so that they look the same, then there is still the question of how much variance there is around that average loss for all the different mini batches. So it's not, if you come back here, there are two terms actually here. So what's hidden behind this LGD, the Hessian of the loss function is already taken into account. So even for gradient descent, it is more difficult to converge to a narrow minimum than it is to converge to a wide minimum. So there are two separate effects here. First of all, it will be easier to converge to a wide minimum, but then given minima of equal width on the average loss, there is also separately the question of how the mini batch random loss functions behave. And that's what is unique to stochastic gradient descent, that it's also affected by this, this extra thing.
Do you want to push on?
So I just wanted to show that, of course, this analysis is very limited, partly because you can think that in stochastic gradient descent, so you start from here, you don't necessarily just keep increasing the variance of that distribution where you can end up, but maybe some of the trajectories go in this region of the space, some other parts go in this region of the space. So reasoning about the mean of these bimodal distributions or multimodal and weird distributions in parameter space doesn't really make that much sense. So it's a good indicative analysis, but it has limitations as to how much it can explain about stochastic gradient descent. One other thing that I wanted to talk about are the different improvements or variants of stochastic gradient descent. And one particular method that a lot of people use, and it's kind of the default choice when you first do something with deep learning, I think these days, is Adam. And Adam has two motivations. The first motivation, and I'm going to, I think, switch to drawing again, because this is much better illustrated in a drawing. So the first thing that that we want to do in gradient descent is called momentum. And the typical problem that it solves is that if you have in the loss function, so now I have, say, W2 and W1, I have two dimensions of the parameter space, and I have a very narrow valley. So my loss function, the set functions for my loss function or level sets look like this. So let's say that there is a minimum here, but you have this very elongated shape of a valley around that minimum. The problem that usually occurs here is that if you run a gradient descent, even just normal gradient descent starting from, say, here, the gradients that are perpendicular to this valley are going to be much larger than the gradients that are pushing you along the valley. So what tends to happen is that you can just nicely converge here. You're going to start oscillating like this, because every time you hit the wall, this is you can imagine this as being the wall of a canyon. The gradients here are going to be very large, perpendicular to the valley itself. So you end up in this oscillating behavior like this, and this means that if you set your learning rate too high, then these oscillations are going to, again, propel you out of the vicinity of this minimum. You won't be able to converge because eventually it's an unstable oscillation and you're going to be sent somewhere else. In the other extreme case, if you want to reduce the learning rate sufficiently so that you no longer are affected by this, this oscillation, then if you shrink the learning rate, you're also going to be converging extremely slowly to the minimum. So you're no longer going to be bouncing off the walls, but you're going to be very, very slow in converging to this minimum. And so what Adam and momentum methods do is that instead of using the gradient in each time step, you calculate a moving average of the gradients. So MT is going to be beta times MT minus 1 plus 1 minus beta times the gradient at times t. So this is the hat of WT dt. So this is the stochastic gradient potentially here. I'm just calling it GT. And instead of using this gradient to update your parameters, you're just updating this exponential moving average. And then when you're updating your parameter, you're going to update not with the gradient, but with this moving average, MT. And what the effect of this is going to be is that if you have these gradient directions in which the gradients keeps changing the sign, so sometimes it's pointing this way, sometimes it's pointing that way, you are going to average this out in this averaging step. And then you're going to make much smoother progress towards the minimum. So this is the idea of momentum. And in Adam, there's a second idea, which is adaptive step size. And this is a reaction to the observation that if you have a loss function like this, generally speaking, the gradients in this direction are going to be larger in norm than the gradients in this direction, because the loss function is flatter along this dimension and it's sharper along this dimension. So when you run gradient descent or stochastic gradient descent, you're going to tend to move a lot more along those dimensions that have higher gradient norm on average, and you're going to have very slow progress along the dimensions where the gradient norms tend to be smaller. And so what Adam is trying to do is it tries to estimate on the fly the norm of this gradient, similarly to how it estimates on the fly the average of the gradient. So we are going to have this VT term, which is going to be beta times VT minus 1. So it's another exponential moving average plus 1 minus beta times. Here you're going to have the squared of the gradient. And square here means squaring component-wise. And so this VT contains an exponential moving average of the square of the gradient. So this is the gradient magnitude, essentially. And this is a vector, so it has these different gradient magnitudes across each of the dimensions of the parameter vector. And then, so if this is the first formula, this is the second formula. The third formula is once you have you estimate the mean gradient and you estimate the mean gradient magnitude, the way you update your parameters is going to be taking an opposite step of the average gradient, but then you normalize by the gradient magnitudes, and you have to include a little bit of a small constant here, because if this gradient magnitude becomes too small, then you're dividing by a small number, and this becomes undefined if it's 0, or it becomes unstable. So this epsilon is just a small constant. So this is essentially the whole point of Adam. It's very simple. It essentially estimates on the fly the first and the second moments of the stochastic gradients, and then it uses those in order to update your parameters. And I'm going back to my slides.
There are a couple of minutes before time for it. I have to go to a NeurIPS board meeting at 3, but I think you want to just push on, and if I drop out, I'm going to make.
Sorry for sort of
no, if
coming up to the end.
Sure, actually, it's all good stuff.
I just want to still include the punchline about this, which is Adam is very good in practice. A lot of people use it because it works very well out of the box without little tweaking of the learning rate and little tweaking of all the parameters. It tends to find a minimum relatively quickly, much more so than vanilla versions of gradient descent. However, as this paper found here, the marginal value of adaptive gradient methods in machine learning, Adam, even though it's better at optimizing, it hurts generalization performance. And it hurts generalization performance exactly because it makes it easier for SGD to converge to minima like this. It's essentially designed partly in order for SGD to be able to tackle tricky situations like this. So while vanilla SGD prefers to converge to this minimum and really would never choose this minimum, Adam is actually much better at finding minima like this, which may not generalize as well as the ones that SGD finds. And so there is a similar example of a recent workshop that's called I Can't Believe It's Not Better workshop at the big machine learning conference this year, where there was another example of a very, very advanced stochastic optimization method that's even more complicated than, much more complicated than Adam. It converges much faster, but is just too good at optimizing, and it actually doesn't work when you try to apply it to deep learning. So the summary from this presentation is that gradient noise is not a bug, it's a feature, it's a good thing, or at least it is now understood to be a good thing that helps you find solutions that generalize better. And it looks like what's happening is that SGD avoids regions in which there is high levels of gradient noise, which might also be regions which do not generalize as well. And one kind of take-home message is that improved versions of SGD like Adam may not actually help. It may help with optimization, but ultimately it might hurt generalization performance. And more generally, an optimization algorithm can be too good for deep learning. So if you try to fix the shortcomings of stochastic gradient descent, you might accidentally get rid of a key ingredient of the magic the magic sauce that makes the whole thing work so well. So that's, I think, the moral of the story from some of these examples like Adam and this more advanced optimization method. So that's where I'm going to leave it. And I can stay a few more minutes if people have questions. And yeah, eventually I will share the notes with more detailed explanations of some of the things that I skipped over.
I thought that was excellent, Ferenc. I'm now in 2 meetings, so I have to switch. Fortunately, one's in Google Meet, so you can do that 2 at the same time. But it's a bit confusing now. I've got another meeting in the air, so I'm going to drop off, but I'll make you host in case people have additional questions they want to ask, and I'll get the video up as soon as it's finished preparing. Ciao, ciao.
So David says, it's just a comment.